Here are solutions to homework set number 9 for ECE 376. In this homework set, we look at INT interrupts, as well as timer 0, 1, 2, and 3. So the first problem is measure how long it takes to hit the button 10 times. To do that, I'll use a little C program. So the first step is to get timer 1 working. So the timer 1 interrupt, all it does is increment a global variable time that keeps track of timer 0 interrupts or overflows every 6.5 milliseconds. In the main routine, here's the little test code. All I do is display the time plus timer 0. That should be displaying time to 7 decimal places. If I compile that, compile and download, this is what you see. So this is the time in seconds measured to 100 nanoseconds. So it looks like timer 0 is working. Now that that works, let us turn off that one. While 0 means this never executes, here's the main routine. I'll record the time when I start, wait till I hit the button 10 times, record the time when I stop, see how long it took to hit the button 10 times. So again, compile, download, I'll hit button 0 as fast as I can. Every 10th time I hit it, it'll display the time elapsed. So it's about 1.39 seconds reading it 10 times. That's the first problem. The second problem is how long does it take to hit the sequence 314157. So now modify the main routine. I'll wait until I hit RB0, that starts the key entry. I'll then wait till I hit 314157, record the time at the end, display the difference in time. So here's what that looks like. 0, 314157. That was 2.8735914 seconds. Try it again. 314157. 3.7506173. So with timer 0 interrupts, you can measure time insanely accurately. Problem number 2. Let's generate a 100 Hz square wave using RC0 and check the frequency with a wire we want. So with this code, this is just a C program. It just keeps on looping, toggling a pin. Measure that pin with a frequency counter and get 100.8 Hz. Okay, that says this is working. Now that that works, let's use INT0 interrupts and timer 0 interrupts to measure the frequency. In this case, I'm going to use timer 0 to measure time in seconds, edge interrupts to measure edges. If I count edges per second, I get hertz. So here I've got a problem. I'm using the main routine. I'm using C code to generate the square wave. I'm using C code to display the frequency. I can't do both. If I use interrupts, I could do both, but here I'm just using just C code. So what I'm going to do is just generate 400 cycles of a square wave. When I'm done, display the recorded frequency. In the background, I've got the interrupts running. INT 0 just counts edges. Timer 0 counts seconds. This has a prescaler of 256 because it can't count to 10 million. Timer 0 is a 16-bit variable. The biggest it can count to is 65,000. But 39,000 times 256 is 1 second, 10 million. So this gives me 1 second. So every second, timer 0 kicks in. When it kicks in, it records how many edges came by. That's your frequency in hertz. Resets the counter. And the main routine, every 4,000 cycles, display the result. So here's what I see. I've got C0 connected to B0. B0 is my input. C0 is my output. This is my frequency. It's between 100 and 1 and 100 hertz. Updated every second. That's one way to measure frequency. Second way to measure frequency is instead measure clocks per cycle. So here's my square wave. If this is an INT interrupt on the rising edge, I'll measure how many clocks this was. So So here's that code. I've got two interrupts running, timer 0, int 0. Timer 0 keeps track of time, just like in the first problem. int 0 looks at edges. Every time there's an edge, record the time of that edge. Remember the time of the previous edge. The difference in time is the period. Then the main routine just displays the period. So here's the code, same as before. Generate a square wave. After, in this case, only 6 cycles, I'll tell you what the period was. The period was dt, converting to hertz. It's 10 million cycles per second. This is how many clocks, 10 million clocks per second. That's your frequency in hertz. Now, instead of just having it good to 1 decimal place, it's good to actually 1 part in 20,000. That's the period in clocks. So I can see that fractional frequency. Both methods are perfectly valid for measuring frequency. In this case, actually measuring clocks per period is more accurate than cycles per second. Problem number 5. Generate 4 different frequencies at the same time. Here I'll use 4 different interrupts. I've got timer 0, timer 1, timer 2, timer 3, each running at different frequencies. Each has a different value of n. N is 10 million divided by 2 times hertz. To implement that, I'll have 4 interrupts running. So here's the interrupt service routine. Timer 0 interrupts every 45,000 clocks. This is just kind of a fudge factor. How many clocks does it take to get to this line of code during an interrupt? Timer 1 is 40,495 plus a fudge factor. Timer 2 is just timer 2. Timer 3, get a fudge factor. These I found by trial and error. As you go further down the code, it takes more clocks to get that line of code, like these numbers get bigger. Initializing, let's turn on all the interrupts for prescaler 1. Timer 2 is for A is 12, B is 199, C is 16. And the main routine doesn't actually do anything. The interrupts do all the work in the background. The net result is I now have 4 frequencies playing at the same time. And to illustrate that, and it'll show off too well, I'm going to connect a speaker to the different wires. So here's C0, C1, C2, C3. I'm outputting 4 different frequencies at the same time using 4 different interrupts. Problem 6. Now let's use PWM to output 3 different voltages at the same time. To do that, for the flowchart, each interrupt has its own flowchart. The main routine just keeps on looping, setting the values of the pulse width, displaying on the LCD. Timer 2 interrupts every millisecond. It sets RC0, 1, and 2, and then sets up the subsequent interrupt for timer 0, 1, and 3. So this is the set. That's on timer 2. Then sometime later, these interrupts kick in and clear. So by varying this time, I can vary the pulse width. What the code looks like as follows. Timer 2 sets all 3 pins. 7 is 1, 1, 1. It sets up the timer 0, 1, and 3 interrupts and clocks in the future. When they kick in, it clears. Turn on all the interrupts. Set timer 2 for 2.5 milliseconds. Then the main routine. This is the duty cycle. 100% is 25,000. That's 2.5 milliseconds. Once I have these, I can display ends and measure the voltage. If I measure the voltage on the 3 pins, I can see that the voltage is, when it's 90%, 50%, 10%, 4.53, 2.52, 0.52 volts. When it's 30%, 90%, 40%, these are the voltages. Basically 30, 90, 40% of 5 volts. So we can fake an analog output by using pulse width modulation. That's actually a very common trick that we use in embedded systems. Anytime I want to output an analog voltage, probably the easiest way is to use PWM. Okay, to illustrate the PWM, you can use a voltmeter. So this displays the average voltage. DC is average. So if I measure it on RC0, this is 4.3 volts. Just back up for a sec. This is 100%. That's my power supply, 4.9. This is 90%. 50%. 10%. So DC measures average. I can also measure the AC voltage. So this is the AC voltage at 10%, at 50%, at 90%. Basically, AC doesn't tell you anything. If you think about it, AC's got 3 units, peak to peak, peak, and RMS. This is telling me the RMS voltage. If I think of peak to peak, the peak to peak voltage is always 5 volts. This is a square wave going between 0 and 5 volts. The peak to peak doesn't change. That's the AC voltage. Really what you want is DC voltage. So there's my percentage. And what that tells me is I can vary the percentage of on time. And you might be able. So that is homework set number 9 for ECE 376. Timer and INT interrupts.